Having studied electricity and then studied magnetism, our next thing is to study electromagnetism, the connection between the two. A current can create a magnetic field, and it's natural to wonder, does it work the other way? Can a magnetic field create a current? No-ish. Experiments by Michael Faraday, among others, indicated that while a steady magnetic field does not create a current, a changing one can. He actually investigated several different configurations to see how that worked. This type of current is called induced current, and the phenomenon is called electromagnetic induction. It's driven by an EMF, but not the type of EMF we've studied. It is, as you might expect, induced EMF, also called motional EMF, because it comes from motion of the wires or of the field. Consider a conductor being dragged through a magnetic field as shown. The right-hand rule indicates that the positives in the conductor will feel a force upward, and negative ones will feel a force downward. Eventually, they gather on the ends of the conductors. But charge separation always leads to a voltage difference, so we've created a voltage difference across this conductor, an EMF. Right, as we drag this, there are, remember, positive and negative charges that are being moved somehow, and as they move this way through a field that's into the page, there would be a force up. That's, of course, the positive charges. And so we get this kind of steady voltage difference across this thing just because it's moving. Notice there's no battery or anything hooked up here. It's just from the motion. As the charge builds up on the ends of the conductor, the imbalance creates an electric field opposing further motion. Eventually, that force equals a magnetic force, and no more charge flows. And we can do the math of that. The electric field from this induced potential is equal to the magnetic force. So Q times E is QVB, because remember, magnetic force, the electric force is Q times the field. Magnetic force is Q times the velocity times the field. And then we can say, well, this is delta V over L. QE is delta V over L. Or electric field, sorry, is delta V over L. And then we have that equals VB. So the voltage across the ends is QLB, where L is the length of the conductor that runs perpendicular to the field. Be careful here, this is an L. This is terrible type choice way back in like the 1700s, that too many things look like this symbol, but it's an L here. There's a reason I'm not using capital L that will come apparent, but much later in the chapter. All right. Batteries generate what we'll now call chemical EMF because the chemical reactions do work on charges. Moving conductors generate motional EMF because the motion causes work to be done on the charges. If we provide a conductive path, this EMF will produce a current, a so-called induced current. The moving conducting rod acts like a battery, sort of, and causes current to flow, in this case, counterclockwise, because we have, as we said before, we're moving this way, so positive charges build up here, but if there's a conducting path, they don't like being here, so they move out along the wire and come back, and then the whole cycle goes on. We assume the wire has some resistance, and therefore we can get some current out that we can figure out. Of course, now that there's a current in the rod, it will interact with the magnetic field as well. It should be pretty easy to convince yourself that the field produces a force that points leftward. In other words, the magnetic force produces a magnetic drag on the moving rod, which would cause the rod to slow unless we exert a force to counteract it. It's the work done by that force which provides the energy for the current. So how do these things start flowing? Because we do work on the rod to move it. We can easily compute the force needed to keep the rod moving at constant speed, because the force we pull with has to equal the force of the magnetic field that exerts. So it has to equal ILB, but remember the current was VLB over R, and so we end up with the force that we have to pull with is VL squared B squared over R. We can see that the drag force is proportional to velocity, so it behaves a lot like air resistance, where the drag force was proportional to velocity. This is used on things like magnetic disc braking systems, which can slow things down without having to use mechanical systems that are prone to failure. All right, the three rods are non-magnetic but conductive. In this case, copper is more conductive than aluminum, which is more conductive than brass. There are three powerful ring magnets, one surrounding each rod. If the three magnets are raised to the top of the rod and released, which one will reach the bottom first? We saw earlier that the drag force is inversely proportional to the resistance. Since the rods are the same shape and length, the resistance depends only on the resistivity, which itself is inverse to the conductivity of the metal. Copper has by far the highest conductivity, so the copper rod has the least resistance and therefore the largest drag force, so it takes the longest. Contrariwise, brass is the least conductive, so it reaches first. And this video is online to look at to see it as proof. We can compute the mechanical power delivered by the pulling force. That power is F times V. Power is always the force times the instantaneous velocity, really with a dot product in there if they're vectors. But here we're pulling, we have a force aligned with our velocity, so the dot product is just their product. And when we put all that stuff together, we get that the power is v squared, L squared, B squared over R. So there's a lot of square stuff in there, which is interesting. We can also compute the power that would be dissipated in the rod, because that would be I squared R. And I squared, remember, was VLB over R, and we squared that. And we see, of course, not surprisingly, the two come out to be the same, because the power that we're putting in is the power that's being dissipated in the rod, so that's to maintain the constant speed. There's no increase in the bulk kinetic energy. It's being thermally radiated into or by the resistor. All right, a device that converts mechanical energy to electrical energy is called a generator. Our rod and field is a generator, but not a very good one. More practical generators use a rotating coil, something like this, where you have a permanent magnet, and you spin, you use some mechanical thing to spin the coil in the magnetic field, which changes how much field is piercing it, and so we get out an EMF that looks sort of sinusoidal. That diagram might look a little familiar. It's nearly the same one we had for an electric motor. There, we turned electrical energy into mechanical energy. We ran a current through, and it caused the coil loop to torque, so we could spin the coil loop. Here, we turn mechanical energy into electrical energy by mechanically spinning the coil rod and generating a current in it. In fact, every motor is a generator, and every generator is a motor. Not necessarily equally efficient in both directions, but always true. The rotation loop makes things a little bit more complicated, because the EMF value varies sinusoidally, reversing direction twice a cycle. This generates what's called an alternating current. Commercial and residential electricity is mostly AC these days, pioneered by Thomas Edison. It beat out DC transmission, which was advocated by Nikola Tesla. All right, square conductor moves through a uniform magnetic field directed out of the page, which of the figure shows the correct charge distribution on the conductor. We do right-hand rule where we have the charges are moving that way. There's a magnetic field, I'm going to pretend here, out of here, and so we can see that the output would be this way. We end up with